Welcome to Baozi Training Leetcode solution. If you want the best mock interview experience in North America, feel free to check us out at baozitraining.org. We have a mock interview for single round and also 3 rounds, plus resume revision. And also feel free to check us out at the blog.baozitraining.org, where we constantly publishing Leetcode solutions or system designs or literally and lots of other things. Cool. So let's get started. So today we're going to talk about this problem called coin change. Essentially, given an array of coins, each coin has a different denominations and a total amount of money. So write a function to compute the fewest number, the least number of coins that you need to make up that amount. If there's not, if that amount of money cannot be made up by any combinations of the coins, return -1, which is totally possible. This is a very, very classic problem. This brought me my memory back like 10 plus years ago when I was studying in undergrad. This is a very typical problem. At that time, I don't really know dynamic programming. So I think until today, when I first saw this problem, my hunch was, oh, can I solve it using greedy algorithm? By greedy, what I mean is really, for example, the coins is 1 to 5. It's not necessarily sorted, but let's just assume it's sorted. Let's assume we sorted and then amount is 11. I always want to see, okay, if I always give the largest denomination to the solution, would that work? So basically I was trying to give more like a 5 and 5, and then now it's basically 1, and then I'll see 1. So essentially my hypothesis, the greedy algorithm, is the largest numbers should appear in the largest column value should appear in the final solution, which is not really the case, right? For example, if you have 1, 3, 4 and the target value is 6, based on what I said, if I'm always trying to fit in the largest number, which is 4, now I have 2 left, and then you'll see 1, 1, you will think, oh, maybe 3 is the optimal solution because 1, 1, 4, which is actually not, because the optimal solution is 3 and 3, it doesn't contain the largest value. So that said, the greedy algorithm doesn't work, but that leads us to a brute force solution, which is list all the combinations of different ones. So this is I didn't really code up that solution, but here is a kind of a solution here. So what it does is, so for all the, it doesn't need to sort, right? So essentially for every single one of the coins here, we pretty much write they pretty much wrote a recursion function. So just keep recursion in as long as the amount is larger than the existing number of values. And then for each of the x is how many x you can actually take without exceeding the total amount. And then you just recurse it in. So just keep doing that for every single value, and then you keep a minimal value. If the result is -1, it means there's no value. So this is basically every iteration you keep a maximal value, and then if it is maximal, hasn't been touched, it means it's -1. So this solution is definitely a brute force solution. And then, so think about what is the time complexity of the brute force solution. It's what it says here is O to the s to the power of n, which is exponential. Why is that? Is essentially think about C means every coin value denominations. For every single one of them, what are the chances? How many numbers of them can actually appear in there? So it is from 0 to s divided by C1. So let's just assume the worst case, right? So s, the total amount divided by the value. So there's this number of chances this can exist. It's kind of like a subset kind of time complexity, right? So this times this, so it's basically dominated by s to the power of n, which is not really ideal. How can we optimize this? So whenever we see those kind of things, because all the values are computed over and over again for the same amount, what we can do is we use a hash map, just like I have many problems listed here, wildcard match. Oh, well, not those ones, but similar ones, right? So you have brute force solution, and then you're trying to use a hash map to memorize the intermediate solution so that when the next time recursion comes in, you don't need to recurse again. So for example here, so before you return, I think here on line 19, after line 19, if I have a lookup table which is a hash map, so the key is the amount, the number of is the minimal cost, and then I add it here into the lookup table. And then before every step of the recursion, I will check the lookup table. If there's already a solution of the minimum value, I directly return. This solution is, I didn't list it, but I have a kind of like similar one. So this one is more like, I have a lookup table, just like what I said, look like this. And I populate the previous value, which is, if you want to achieve each of the coin value, let's say the coin value, the denomination is 3. So how many coins do you need? You need 1. This is like a pre-populated. And then I iterate through all from 1 to all the amount. And then I was basically checking the hash map. Do I actually have the other amount of number? If so, I return it out, or else I do the minimal. So you can pause it here and take a look, but I don't really like this solution because it's not that clean. And then the cleanest solution is actually, by using this, and then we can use DP. The time complexity by using a lookup is actually the same as DP, which is O S times N. S is the total number of amount, and N is the array size of the coins. It's honestly, it's not very obvious from the lookup table solution. So here, if you download the solution, you can also see this is kind of like the recursion tree. But why using a hash map can make it better? It's kind of not that straightforward, but using DP is super straightforward. Let me explain the DP method. So I have many problems I explained already. What kind of problems can we solve using DP, right? So it has to be a single yes or no answer, or asking extreme value. It doesn't want you to return all the intermediate steps, because all else you have to use brute force and then list out everything. Here we are pretty much build up a lookup table using formula. It's kind of like the coding pattern, and here the formula is basically the lookup is for the amount, and the value contains this. The index is the amount, and then the value is the minimal coins needed for this index to achieve this index, which is to achieve this amount. So the mathematical deduction function is for every step, right? Is the minimal of the existing minimal, or it's, let's say my coin value is 5, so my current amount is 7. So 7 minus 5, so what is the minimal steps of 2, and then plus 1. So given I minus coin value larger than 0, or else the array is out of index, or else it doesn't make any sense, right? And then this has to be wrapped into a for loop. So here's the dynamic programming part. So if I actually have a graph here, so let's say you're trying to achieve 11, right? So essentially, what are the amounts? The amount would be 0, 1, 2 until 11, and then this vertical part, the column part, is the array list, the coin list, which we have 1, 2, 5 as denominations. So just as a normal recursion, we always want to list a kind of like the initial value first. So how many coins in order to achieve amount 0? So it's pretty much everything is 0, 0, and then this is 0. Now we basically see, okay, how many coins do we need to receive a amount 1? So we have to go through all the, so we have to have a for loop that we go through all the every single values, and then we compare, okay, whether my existing values is the minimal or this amount minus this value. Let's say 1 minus 2, but in this case is exceed 2. But let's say if we're talking about 5 cases. So what we'll do is for 5, so what is the, for 1, like what is the number of values? For 2, so 5 minus 2, what is the existing number of values, the minimum ones, plus 1, of course, to achieve the amount. Okay, and so that said, the code looks like this. First, we need to allocate an array, amount plus 1, and then 0, of course, is 0, like I explained. So now we need to build up this table, right? So for each of the iterations, so until we reach the amount. So let's say for each of the iteration, we have this minimal value equals to maximal value to remember this. So for each of the coin, if my remaining amount, which is index, is still larger than coin, and also this other part, I minus coin not equals to minus 1, because if it's minus 1, it means there's no solution. You don't even need to look into this. So that pretty much default to the line 16, which is if we never touch the minimal, so we should assign the value to be minus 1 or else minimal. Because there is not a solution using existing coins, we can achieve that number. So what we do is we always choose the minimal value between the existing minimal or between this value minus the existing coin plus 1. So back to my 5 case. So is so first of all, we have a minimal, right? So this is the equals to integer largest. So what is the first thing is basically if I take one coin of 4, so what are the minimal ones between 4, right? How many coins do I need to achieve 4 plus 1 given the existing minimum? How many steps do I need to 5 minus 2 is 3, right? So 3 plus 1 because I only need 1 coin. Or if I have a 5, how many do I need for 0? So in this case, it's pretty much is 1 because all you need is only 1 coin. That is the minimum value of 5. So this building up this is very straightforward. So this is S, how many values, and then this is n, array size. So that is S times n for time complexity. It's the same with using the hash map one. And the space complexity is ON because we use a lookup array. It's a medium question, but it's a very classic question. I would highly recommend. So next time you say, oh, well, what is the minimal number of coins we can use? That's a straight up, actually, DP questions. That's all. Let me see anything else I want to say. Yeah, that's all. So it's a DP. It's relatively easy to think of. It's a classic one. But if in an interview, I'm thinking if somebody asks you this question, you directly come with DP, which is also fine, right? So you can talk about the recursion one first. But it's kind of hard to code the recursion one. You can just say, okay, I know this is a DP problem because it fits all into the DP part, and then yeah, should be good. I mean, it's not really a good interview question because it's about algorithm, but DP really, I mean, in real life, we don't really use it too much. And it doesn't really test any kind of your coding ability. If you know this, the code is actually quite straightforward. So not a good one, but good to know. All right, see you guys next time. Leave any comments if you have any questions. Bye.